bad whenever I get like what's called like a bad grade because I'm both trying to like use my uh use my knowledge and check at the same time. And it's like whenever people are like, yeah, how did you feel? Like I got 90. I was like, oh, that's you. That's not me. That's you. I can't. Plus, I get really nervous. Like the way my stuff is set up, like I always set myself up. But the way I'm seated, like it was like right there. Like,
That was literally like
yeah, I
right in the
know.
corner.
You and the girl next to you, the girls next to you, you guys have like probably like the better spots. Yeah. You and both? Indra, yeah. You guys probably have the better spots.
And before Alex would come on every single time. I was like, I don't know a lot of the stuff because I skipped his investment course. I'm gonna take it in the fall.
No, I told him I was like, hey, dude, like I'm mostly like not like I'm not business at all.
He knows
So,
too.
yeah,
Everyone
like
in my class was either a finance major or an accounting major or what's the name, an education major in this finance class, and I was like, I'm math. Like, hey, yeah, I'm the one
I
math,
told him straight up,
the
I'm
one
like,
math
listen,
student
if
in
I
there.
saw it, like, that's enough.
Do you have any questions?
I think so. You have one. I think I have one. I've actually did some new homework.
Okay.
Yeah, because I like the notes that you post because I didn't go to I think I didn't come Tuesday, but I looked at the notes and I was doing the questions that you posted.
I started making a recording of the class. So just in case anybody knows the class, you can scroll down. Georgia View, you scroll down to class recording. I think it's actually the platform on Clever Ultra. They normally have the recording over here. That was from this Tuesday. That's Tuesday. I try to label the recording so you can kind of see what was going on that day. Um, I'm not sure how long they're gonna keep the recording there because they've been telling us that they might take away our recording. That's why I stopped doing the recording at the beginning. But then I realized since we every day there are students that were not here, so having the recording there gave us a backup plan for if in this class we can still have a way to check out what was going on during the class.
I'll formally complain if they take the recordings.
Yeah, like,
I'll be like,
it's
I need
helpful.
it.
Yeah, I think it's helpful to like have recordings and stuff like that. Even if
Yeah,
like
even if I'm
it's in
here.
the class,
Yeah,
like it's good to go back.
Right, you can go back and see what was that again, right?
Yeah.
Well, you said you have a question?
Problem 8 on 3.2.
Okay. To number 8. Let's see. This is mostly applying the annuity immediate formula. You can see after a little while you realize the formula is very helpful. It makes analyzing things a lot easier. Suppose you have annuity each of which you have 3 annuities, each of which make payment 1 year from now. Annuity A will pay $1,122 every year. Annuity B will pay $1,020 every year for twice as long as annuity A. Annuity C. You see, for each of these, we don't know the length. We don't know how many payments, right? We know the amount of payment. We don't know how many. But we do know for B is twice as long for annuity C, which pays 1,270 every year for 4 times as long as A. The present value of the annuity B is 35% greater than that of the present value of annuity A. All of the 3 annuity will earn interest at the same rate. So they have the same interest rate. So there are quite a few unknown things in here. We don't know the number of payments, we don't know, or the number of years. And we also don't know the interest rate. But we also are not trying to find them. So we'll try to find a way to model the relation between them. So It looks like the question is concerned with the present value. So the formula we'll be using will be the A formula. And you remember the A angle N for the present value, then the S angle N for the future value. So obviously we are concerned with the present value. Let's write the formula. The formula for the present value of an annuity is N is number of payment. I is the interest rate for each payment period. The formula goes 1 minus V to the power N. V is actually the 1 plus I to the power -1. So this is really to the negative N over interest rate I. So we're going to keep using the same formula and try and write the formula over there. So for the first payment, let's say annuity A, for this present value, this is a present value if you pay $1 each time. This is an end payment of $1. And then your total present value before at time 0 is this. Okay, so now for A we have $1,122. So it's going to be 1,122 times A N I. Just want to use a formula to simplify it. For B is this. B would be B has a present value. I guess I should really write the present value notation there. Okay, so for A it goes present value equal to this. Because you're not paying $1 at a time, you're paying $1,122 at a time. For B, we're gonna do the same calculation except the payment is different and the length of the payment. So this is going to be 1020. This is how much we're going to pay, and that's going to be multiplying our annuity formula. Present value for annuity with $1 each time is ANI. Now in this time it says twice as long, so we actually have 2 and twice the number of payment. So if this is being paid n time, this must be paid 2n times with the same interest rate. Okay. Because even though we reduce the number of payment each time, that we make a longer payment. So of course this should have a higher present value. Of course, according to what's stated, the present value of annuity B is 35% greater than the A. So we'll say this is a 1.35 of the present value that was the last question. A little bit more space. And that's the model, that's the equation for B. Are you okay so far? I try to write with the notation because this is really a lot shorter. Otherwise, the whole A and I, you see how large the formula is. And next step, we probably have to write it out for C. We just want to have a general idea what's going on. The C says it pays 1270, and we're paying even longer, 4 times as long. So your length of the payment is going to be the same formula, except n is going to be higher. So the start is 4n, 4 times of the interest, 4 times longer, but for the same interest rate, which we don't know. Okay, well, what did C say about C? And the present value B is 35% greater than A. All 3 annuity will earn interest rate. What is the present value now of the final payment of annuity C? So we really don't know that. So from what we have, you can see that we can definitely determine a relation between A and B because they have a ratio. But C, since we don't know that, we don't have any additional information. I guess for C, what we really care is not the total present value, is what was the present value of that one last single payment. So we're trying to find the present value of the final payment. So what was the final payment? Each time we're being paid 1,270, right? That's how much payment we're being paid. So we want to find the present value of this. So you see, if you're looking at a timeline, this is time 0. Now this is the time 4n. So at time 4n, you're paying 1,270. To find the present value, you have to discount it, right? So we're going to discount it. So the actual present value for that 1,270, this is, you're going to divide. So the final payment payment, the present value is equal to 1,270 divided by whatever the interest rate, it's 1 plus I raised to the power of 4n. 4n. That's really the concern. So what we have here is we don't know the I and we don't know the n. 1 plus I to the power 4n has to be divided by 1,270. So then we would find out the present value. So it should be a lot lower than the 1,270. So now we're going to utilize what we have for A and B to somehow find a relation between A and I. All we have to find out is 1 plus I to the power n. What was that? So we're going to really look at these two equations. So all these analyzed just to figure out what was the focus of the question. Now, one thing is for sure we don't know the present value, so we're going to divide these two equations. That way the present value will be gone, right? So we're going to divide the A equation with B equation, so kind of like this. If you take the equation B divided by equation A, and then you end up getting this, you're going to B divided by A, then you have 1.35 on the left side. On the right side, you have 1,020 divided by 1,122, and then also we have this formula that A2NI is divided by ANI. Okay. And then the rest is all algebra. Let's see, this is equal to 1020 over 1122. The top one, it goes 1 minus 1 plus I to the power of negative n over I. So that's the an, oh, there's 2n. 2n over I. And the bottom one is going to be 1 minus 1 plus I to the power of negative n over I, but then you divide, the division of division is actually multiplication of I. The I part is really canceling out. We okay there? So it looks like it's, we try to solve something out of this. We cancel the I, this cancel this, and then we can divide both sides by the coefficient, which then gives you 1.35 times 1122 divided by 1021, which equal 1 minus 1 plus I to the power of negative 2n over 1 minus 1 plus I to the power of negative n, right? So it looks pretty complex, so just to make it easier to solve, let's name a new variable. Let's make x equal to the 1 plus I to the power of negative n. Or this will be like a 1270 x to the power 4, right? Then, so if you solve for the x, that's right. This is the 1 plus I to the power negative 4n. If you have 1 plus I to the power negative n, then this will be x to the power 4, right? So if you solve for the x, and then of course the final solution will be this. So then, the reason I want to name this x is just so the equation is shorter. So if you name the x in this right side of the equation will be now at 1 minus x squared over 1 minus x. I mean, hopefully this will make this equation a lot easier to solve. Are we okay so far? I mean, a lot of times if you simplify notation, it causes the whole equation to be, now you can see the factoring, yeah? Before with the higher power complex formulation, and so this is the beauty of changing the variable. After you change the variable, and then we realize that the numerator is 1 plus x times 1 minus x, right? And denominator is 1 minus x. So it's really possible for us to cancel the common factor. We cancel the 1 minus x. So this is really 1 plus x. Right? Any questions so far? Any questions? You see, in here, it's still factorable. It's possible to see that this divide this out. But then once you turn the format, you really realize you were supposed to divide out. So once you divide out, you realize the x value is equal to the 1.35 times 1122 over 1021. That's 1 plus x. If you want to solve for the x, all you have to do is subtract 1. So the x is 1.35 times 1122 over 1021, and then minus 1. That's our x. And that's what we need in here for the final solution. We okay? So let's see if that works out. So we're like, what was it? 1 to 70. So 1 to 70 is going to be multiplied by x to the power 4. And x is equal to 1.35 times the 1020 divided by 1122. We have the minus 1. That was the x minus 1. And now we're,
I think it's the 1.35 times 1122 divided by.
Thank you. I was like, this is so small, the discounted present price cannot be done. But that would be like roughly $70 present value. I mean, this must be a really longer time. If you got $1,000 in 20 years, the present value for that $120 probably isn't worth that much. So it's reasonable to have that solution. Do you have a different solution? Are we okay? Any other questions? Sorry that my explanation is lengthy. Do you have any other questions? Jonathan, do you have other questions? Okay. So that's the one about annuity. Immediate, of course, there are also annuity, the perpetuity, which is payment that lasts infinitely. So last time, if you watch the recording, you see last time we were talking about outstanding balance and non-level payment. See, having the recording there even helps me, so I can kind of review what was going on last time. There. In annuity, the first section was talking about what was annuity immediate, what was the formula, what was annuity due, what was the formula for calculating present value and future value in a annuity immediate and annuity due. Now 3.5 talking about deferred annuity. So let's say the annuity was for a payment in the future. What was the present value for those payments? Or if you have annuity, what was the future value of those payments after it's already paid out? So if we want to look at annuity, value of annuity at any given date, and this is the one that concerns us. So there's a couple calculations. The treatment are different. Sometimes you can use imaginary payment to subtract the imaginary payment from an actual payment to find the value of a future payment. Sometimes you can also find out the total value of your, like this is the total value of 15 payments with each payment being 5,000. That was the interest rate. So that's what happened in time 25. If you want to find the present value, like find the value at time 18, you have to discount it. So the second method will be discounting the future payment, so then you will find the present value of those future payments. And let's see, those are the annuity, deferred annuity. Now these deferred annuity calculation is to help us understand how to calculate outstanding balance of a loan payment. So let's say you borrow such an amount of money and you're going to start paying it back. And what's being called outstanding loan balance is, let's say you've made several payments. Let's say you've made 5 payments. Now you should owe less than your original loan that you borrowed, right? And you want to find out how much do I still owe money for. It will not be the same thing as adding up all the future payments. It's actually the present value of all the future payments or the future value of all the past payments. So there are two methods for calculating outstanding loan balance. One of the method is it's called the retrospective method, which is calculating future value of all your past payments. And that's what's going on. You made a couple of past payments, and this is subtracted out of your total borrowed loan money. Of course, since this is future value, you have to let the money grow a little bit. The time period, that's what's going on. So this is the retrospective method. You're looking back at what has already been paid, subtract those payments out of your total loan balance. This is the one calculation. This method requires you to know how much money you have borrowed and how much money you have paid. And the second loan balance calculation is called prospective. Let's assume that you are given an annuity, you know how much you're being paid. Let's assume you didn't really calculate how much money that's supposed to be the present value of your total annuity. So which means, suppose we don't know the L, then the prospective method works out if you know how much future payment is. So this is your future payment, this is your last payment, and you discount it to your present time. So this is discounting all your future payments to your current time, which is time K. So at time K, what was your balance, outstanding loan balance? Calculation using the prospective method. Any questions? The method itself involves, see that's the annuity notation, that was the discounting function, discounting factor. So understand the notation is part of the procedure, part of the steps when you try to calculate loan balance. Any question? All right. So let's start. Did we talk about this example already? I think we have already. We did talk about this example. This is a question about, let's say, you are trying to pay back a loan and you're paying $80 every month at the end of every month for 30 months. Right? So you're paying $80 payment. I mean, if you multiply 80 with 30, you're paying like 2,400 there. But the question is, let's say you have paid 12 payments. You made your 12th payment. Now the question is, what was your balance now? And that's a little bit harder than thinking about what's going on. You may want to just multiply 12 times 80, but it's not so simple because you have to take into consideration of the time value. So here are the calculation. Since we don't know the total loan, we only know the payment. We're actually working with using the prospective method. We know all the payments are 80, so we're looking at this model. So the calculation is 80 times the payment, 18 payments, each payment is 30. 80 times A corner 18 with interest rate 0.04. Any questions? The rest is applying the formula. So this is a annuity formula. I hope that sounds familiar. 1 minus 1 plus I to the power negative n over I. So that's applying the formula. to find out the $1 payment present value, and then you times 80 to find the total present value of all your $80 payments. So we are still owing 1,380 on the balance. So, any questions? Same, similar. I think there's another example. This question: suppose we have a loan of 20,000. Now that's our L. We know our loan amount, and then they're being paid with $2,500 payment each year. The last payment is slightly lower, which we don't know how much lower, and that means we're gonna have to use the first formula for the calculation. The retrospective method is meaning that you know your past really well. You do the retrospective method. If you want to use prospective method, you have to know your future really well, like what you're supposed to pay. In this case, the final smaller payment, meaning that we don't know what payment, we don't know the future as good as the past. So we're going to use the first method, the retrospective method. The question is find out the outstanding balance after we made a payment totaling 16,000. So the method is we want to find out how many we paid. This divided by 2,500, we realize we made 6 payments. So we're trying to find the outstanding balance at times 6. So we made, right after we made 6 payments. So you take your loan amount 6 times here. You take your interest rate plus 1 raised to the power 6. That's how much it worth. That's how much the 20,000 worth at time equal to 6. At t equal to 0, it worth 20,000, but at t equal to 6, it worth this much. So gross of the money, and you want to minus the present value of all your payment that you just made. We made $2,500 payments, 6 payments. The future value, and we don't want to go back to the past. We want to find the value at time 6. So at time 6, this is how much it was. And then we follow the formula for the calculation. This is a balance that we have. Any questions? So we might have to consider both of these two methods, which one is more convenient for the purpose for the calculation. All right, 3.7, 3.9, 3.8, these are 3 sections, non-level payments. So that is when you are paying not the same amount, not level payment anymore. So I kind of group them all into one assignment. Some of them are easier, some of them are harder, and depending on how we look at it. So we're going to start with the one that doesn't follow any formula. Then you may have to look at the. I feel like we talked about this already, Jonathan. Did we do this one already?
I wasn't here last.
Okay, who's here? You are here.
Yeah, I don't think we did this.
Oh, okay. Non-level annuity. So let's see if the payment is not the same, what do we do? Well, we did the same as what we were talking about in chapter 2. Now we studied the timeline.
3.7, yeah, we did.
We did this one. I feel like I was talking to somebody last time when we were going over this.
Well, I don't think we finished the chapter, but we probably went like halfway. Let's see, like example 3.72.
Okay. All right. So I think looking at the timeline and really look at how money go is kind of a common method to the chapter 2 and chapter 3. So here we're looking at July 1st. We win a lottery. The price is a 20-year annuity due with payment of 1,000 each. July 1st, and payment 2,000 each January 1st. So the payments are not the same, but then you realize some of them are actually the same, some of them are not the same. So what is our treatment? It's actually treating them as 2 separate annuities. In each annuity, they actually have the same. So you can see every July we get 1,000, and every January we get 2,000. So the 1,000 payment for every July for 20 years. So you have 21,000 payment. You also have 22,000 payment. So you can think of this payment as there's a number of payments, so it's n. So you have 1,000, and you use annuity immediate or either way. I think we can do either way. We can payments July, and then all left to accumulated accounts. Yeah, I think you can use either annuity due or annuity immediate. I would prefer annuity due. I would prefer annuity immediate. So anyway, this payment you will find the total sum time 20, and this payment you also want to find the total sum at time 20 with this one. You have to let it grow a little bit. There are 6 months. You have to let the money grow for 6 months there. So one of the payment, you have to look at the time payment, time difference. So here we are. So that 1,000 payment, this is the annuity view formula. We're going to find out the total value or future value, which is this much. And then for the 2,000 payment, which also is 20 payment with the same interest rate, and you let it grow a little bit, like half a year interest rate, let it grow a little bit bigger than what it is. This is the value at time 20. So the 2,000 payment was for January. So if you want to find the value on July, that's half a year. So the interest rate has to raise to the power 1/2. So that's what's making it slightly bigger. And then we add these two together. That's the total value of the both annuity. Any question? This one. All right. 372. We have annuity of the last 12 calendar year. At the end of each quarter, there is a payment. So meaning that you're being paid every 3 months. The first quarter we're paying $200. Second quarter is $300. Third quarter is $150. Fourth quarter is $400. So every quarter they're paying differently. But then every year they're repeating the same pattern, right? Next year, first quarter, second quarter, third quarter. So you can actually find the total payment each year and consider that as an annual payment. Right? You can combine all these payments to one single payment, one single last year end of year payment. And then we can probably look at this using annuity immediate formula, and that's the plan. So we're going to take the 7.2 interest rate divided by 4 to find the quarterly payment interest rate. The quarter payment interest 0.7 nominal quarterly interest rate. So 7.2 is being paid quarterly. So 7.2 divided by 4, that's 1.8%. So every quarter the interest rate is we want to find the end of the year. So from March to the end of the year is 3 quarters. So your quarterly interest rate raised to the power 3. Now, this is the end of June. So by the end of June to the end of the year, you have 2 quarters left. Power 2, that's the quarterly interest rate. So this is the 1 quarter to the end of the year. And this is already at the end of the year. So this is the total value of all the payments by the end of the year. Their value is this much. So even though we're being paid quarterly, it will be the same as being paid every end of the year with this much. And we're being paid for how many years? 12 years. 12 years. So it's kind of like an annuity immediate. We're being paid at the end of the year Y amount. Y is being calculated. Y is at $1,074. And you're paying for 12 years, and then your annual interest rate is I. The I you have to calculate it convert it from quarterly interest rate into annual interest rate. And then you can find the future value using the future value formula. Any questions? Right, so S is our formula for the future value of the annuity. A is a formula that we calculate present value for the annuity. And this is a future value, accumulated value calculation. All right, we also going to look at a couple scenarios where it's easier with our BA2 plus calculator. You can also calculate it with our annuity formula, but this one we're going to show how to calculate it with the calculator. So here we have a monthly contribution. So you're trying to take money into a saving account. Interest rates, we don't have interest rate, we have discount rate. So you may have to turn this discount rate into interest rate, like 1 minus 0.054 over 12 to the power of -12. Remember the relation between discount rate and interest rate? Are you okay there? Do you have questions for how to use the discount rate? Yeah, so we can always convert the discount rate into an interest rate. So assuming we now know the monthly interest rate. Now, first year, how much do we save the money? first year should deposit 600 every month. Okay? Next year, second year should deposit 1,000 every month. Last year it went a little bit different. Last year she deposited 1,200 and then 1,400 and then withdraw 5,000 and then save 2,000 and then 2,200 and then she has 1,600 for the rest of the year, and that's all 2 years. Any questions? So I try to draw everything on the timeline so it will be clear what's going on with the input and output. The question is, what was the balance? What was the balance of the saving account by the end of the 36 months? We have 3,600. So now the calculation, you can do it this way. You can find the annuity immediate future value for the 600 S12, S12I, and then you have then you have to, this is 2 years, so you have to find the future value of this. At 12, at t equal to 12 is 600 S12I, but then you multiply 1 plus I to the power 2, or 1 plus I to the power 24, depending on what interest rate you're using. And then you can see there's 12, there's 1,000 payments. So you have 1,000 A12I, and that's the value of these payments at t equal to 24. And you have to, again, let money grow to find the future value of these. So you have to change your timeline. Are we okay there? Then the rest of them, you have to do it one by one. So if we're finding this future value by hand, it will be a bunch of summation of a bunch of calculations. You may have to turn each one of them to their future value. You get what I'm saying? You can actually calculate it by hand one by one, which is a little bit more time consuming, like 600 times 1 plus I. Let's say we have monthly interest rate times 1 plus I to the power 35, and then 600 1 plus I to the power 34, and so on. You know, calculation by hand it's possible, but it's really time consuming. That's where the formula comes in. Now, with the calculator is a lot easier. So this is how you do it with the VAT calculator. You can use the cash flow, or use this is the cash flow worksheet. You can also use the I think it's also possible to use the other worksheet, the time value worksheet. So you click on CF second clear work and start clear the cash flow table. And now you're going to start entering number into the table. 600 is your first input, and that's, I think it's C. And then it's the C01. And then that's repeated 12. That's the frequency, 12. So that's your first 12 payment of 600. And then you go 1,000, and that's repeated 12 times. So then here we have 1,200, and you will make sure. Well, that's 1,000 payments, and that's 12 payments. And then 1,200 is for that month, and then 1,400, 5,000 negative, and then 2,000. All right, and then the rest of them, they are all 1,600, 7 months, 7 of the same quantity. That finish all 36 months input. After that, you let the computer calculate your net present value. Then you have to identify your interest rate. So this is turning from the discount rate into an interest rate. So you go 0.5054 divided by 12, turning that into negative and subtract out of 1, and raise that to the power of -1. So this is pretty much the process of turning that into your interest rate. Then you can calculate your net present value. So this net present value calculated the present value of all these payments. So it's going to find out what value in here, and then you have to calculate all the way to its future value. So you're going to multiply that. Once you find the present value, you're gonna multiply the interest rate to the power 36. So your monthly interest rate has to raise to the power 36 and multiply your present value, which gives you the future value. And this is the entire, it's kind of lengthy to me, especially all the interest rate times there. If you can calculate interest rate separately on the side, then the process will be a little bit shorter. Any questions? I'm trying to put this in to double check if there is final answers, okay? Before that, from here to here, I'm all okay because that's basically enter all your cash flow. But once you finish the cash flow, you have to deal with the interest rate, and that's where it starts getting a little bit lengthy. A couple of process procedures, try to convert the discount rate into an interest rate, and then convert it from present value to a future value. That's the conversion rate. Do you have any questions? Any questions so far? These are all textbook. You can always double check that. This is part of the textbook solution. All right. Now let's move on to annuity that's non-level and it's not convertible to a level payment. So let's look at the payment that seems to be geometric. Okay, so Roy purchased an annuity immediate with an annuity payment for 25 years. The first payment was $800, and the payment afterwards increased 6% every time. So the question is, what is the price? So, well, you're buying an annuity, and then how much money are you paying it now to buy the annuity? Whenever it says purchase price, it's pretty much a calculation of present value, right? You pay what it was now, even though in the future it may worth more, but that's what happens in the future. So here the purchase price, we assume the interest rate is 7%, but then the payment actually increased by 3% each time. So I have a couple of things: the payment, the initial payment, the increase rate, and the interest rate. So this is payment increase by 6% there. Let's call that G as in geometric progression. And let's call this I. I is 0.7. So here we are. I feel like we've done this before. All right, so this is what's going on. We are looking at a geometric sequence here. So just want to explain what's the process with this calculation. Did I not make a copy of this? All right, so this is the first example in 3.8. Okay. So what's going on is you have a payment that's geometric, and you start with time 0, and here is the explanation. All right, annuity immediate, which is paying at every end of the year for 25 years. So you start from 0, and then 1, and then 2, and then 3, until 25. So this is the length of the payment. And then the first payment was 800. This is 800. Or it says that every payment increased by 3%. So your next payment is going to be 800 times 1.03, right? Correct. And the payment afterwards is going to be 800 times 1.03 squared. So each time it increases a little bit, right? It goes down in that progression. So the last payment will be 800 times 1.03. Guess what's the power this time? 24. So we're trying to find the present value of all these because we're buying it. So we're going to find what was value for each one of these payments. So you can see the first payment, its present value for the first payment is going to be 800 discounted for 1.07, right? Because the interest rate is 7%. And it goes with the same thing. For the second payment, it's going to be 800 times 1.03. But then you have the discounted for 1.07 to the power of 2 because there's 2 times here, 2 years. Are we okay there? So we're going to do the same for the rest of them until the last one It's going to be 800, and then 1.03 to the power 24, which is discounted for 25 years, so it's 1.07 to the power 25 there. So all of these, they do have a common factor. One of the common factor, we're going to find a way to model the total summation. It's a partial summation. It's a geometric series. So 800 divided by 1.07 it is a common factor, and that's what's being factored out there. And then everything else that's left in here is going to like 1 plus 1.03 over 1.07, right? And then we keep doing until the last one is going to be 1.03 to the power 24 over 1.07 also to the power of 24, right? So that's a geometric sum, and this geometric sum is calculated by this. Okay, so that kind of explains the rest. Are we okay? So this is a partial sum formula for a geometric series, and then we realize that this number, if you multiply with the denominator this number, multiply with the denominator this one, that's what's giving us this denominator. So that's going to be part of the formula in the next page. So this is the final calculation of present value for all the payments. All right, so now that brings us to the solution. So we have the idea. Suppose you are making a payment. The initial payment is $P, and every payment is slightly higher than the payment before by G%. So 1 plus G would be the factor you have to multiply to get to the next payment. And then turns out, suppose that I is slightly higher than G. I mean, if I is lower than G, it's not worth doing the whole thing. So I is lower than G, the 1 plus G over 1 plus I is smaller than 1, so 1 minus 1 plus G over 1 plus I to the power n is meaningful. Otherwise this end up being here higher than 1. Why would I want to do that? Because that has negative value. All right, so 1 minus that, which kind of echo what we have already done there. It's a 1 plus T over 1 plus I to the power of number of payment over the I 1 plus I minus 1 plus T, which is the I minus T. So it gives us this final formula for the calculation. This formula has a slight problem that we have to require that the I is higher than G. The interest rate is higher than the growth rate of the payment. Now, what if they're equal? If they're equal, the denominator is 0, then the whole formula does not work. So we can also look at that scenario. If they are equal, then what's going on is that you can see it from here. All right, if they're equal, what's going on is these two are equal. And then the 1.07 is out, and they still be all 1, right? They're all 1. If they're equal, then it's kind of like a level payment. They're all 800, right? Right? So they are all level payment. You can just calculate a regular, the total value is just a regular payment, like any payment of the same quantity. And I explain the total summation if they interest rate are the same. Any questions? Right, so this is a geometric series. Let's look at an example. So in this question, Andrea inherits a perpetuity immediate with annual payment. The first payment is $2,000. After that, the payment increased by 2%. Find the value of this perpetuity on January 2002 if the annual effective interest rate is 3% from January 2002 through January 2009 and 4% after. All right, we're going to have to look at the model. So first we're going to look at the timeline. Obviously, we're being paid a little bit more each time, 2% increase each time. So these are the payments in thousand. I mean, being paid in thousand. 2000 was the initial payment. The interest rate has gone up since 2009. So 2002 to 2009, it was 3%, and it's 4% after. Okay, so we want to find the present value of all these payments. Questions: find the value of the perpetuity on January 2002. So we're trying to find the present value of all the payments. Okay, and so what happened is now over here is a annuity. It's annuity. From here to here is annuity. It's a perpetuity, which is interest-only payment. Okay, so we're gonna have to separate these two. The one for the 3% interest rate and the one for the 4% interest rate, we have to calculate it separately. What's the difference between the one that's finite? If you're calculating a finite sum for a geometric series, right? The rest of them, you're gonna find an infinite sum for a geometric series. And we can use our infinite sum formula that we learned in calculus. Are we okay there? So here we're going to try to model what's going on. It's kind of repeat the same thing from the last example. Here you have $2,000 payment, and then you have a interest rate of 1.03. So that's 2,000 with interest rate 0.03 at present time. That $2,000 is worth this much. That payment, are we okay? Now you do have a payment over here, and discounted for 2 years, and you have this to multiply. So this going on until 2009, this is your payment. You discounted for 2002, 7 years. So the last payment is that one. So the total number payment is 7. So power 7 there. This calculated, it followed pretty nicely with the formula we had already, but with a little change since the number is different. Any questions? Okay, so that is the first half. That's this part. So this part we're gonna do the same. So you're gonna look at these are your payments. You discounted to time 2, and you start from that. You discounted for from 10 to 2 is 8 years. So you discount every single one. So that discount factor is gonna be right here. You discount each payment this much because the interest rate was 1.03 before it turned 2009. And afterwards it's 1.04, so we follow the formula we had there. Except this is the infinite sum, so this infinite sum has a total of this. That's 1 over A1 over 1 minus R. That's the formula from calculus. And the rest of them, they are common factors. Any question? So this is the total sum. We might have to pay attention to how the time is changing onto the end of timeline. It affects how you organize the power. Like this power 7, that's also power 7. That power 7 is to let your money grow. That was 1.02 increase in money. And this power 7 is discount to the present time because we're calculating a present value. So to look at all these power and the exponent and make sure they match your timeline. Any questions so far? All right, 3.9, we're talking about what if the payment is not following a geometric pattern? What if it's not multiplying a factor? What if we're adding a number that's the future payment? Okay, so we have some notation in here. So let's say we're being paid $P at the beginning, and P plus Q is next payment, P plus 2Q is next payment, and P plus N minus 1Q is the last payment. So let's assume that we're paying N time, we're being paid N time with those payments. And this is a so-called annuity with payment in arithmetic progression. Any questions about notation? All right, so this is called IPQA. I represent increasing, so it looks like we have increased payments. P is the initial payment, R is the common difference between the payments, A represents we're calculating initial value of the total annuity. Here the IPQS, I think it means increasing, P and Q are the payments, initial payment and increase common difference. X is the future value. So at time n, the value is this. At time 0, the value is this one. And we're trying to use the notation to simplify our idea and simplify the formula. Any questions? We're going to try to come up with a formula for this. I mean, if you have a formula for this discounted n time period, you will find the present value. So Only to, it always like you find this, you let money grow, you find that. If you find this, and you let money discount it back to the value one way or the other. So they all have always have their own underlying relation. So then it's like focus on calculating this future value. Now this future value, what is the value? Essentially it is this P dollar, let it grow for n minus 1 times it, right? So T times 1 plus I to the power n, T plus Q times 1 plus I to the power n minus 1, and so 2Q times 1 plus I to the power n minus 2, right? That's the total value. So the actual formula for IPQS, this is the formula, and we have a little problem with this formula. You can use this formula for your discrete calculation, but the uncertainty in the formula itself, it made it a little bit hard to use. You get those dot, dot, dot there, and then every question you have to count how many, what was the N, what was the P, what was the Q. So we're hoping to find a common formula to make it easy. So how do we cancel the dot, dot part, the one that's uncertain? So we're going to try to cancel them by subtraction. So you multiply the entire thing in the 3.92, multiply both sides of the equation by I, 1 plus I, multiply 1 plus I. And the goal is increasing the power, because once you increase power, you may have a common term that could be subtracted. So you multiply 1 plus I. This you multiply 1 plus I, you get power n. This you multiply 1 plus I, you have power n minus 1. That was n minus 2, now it's n minus 16, n minus 2. Then we have this. And then we can start working on subtraction. Now, if you turn this one, subtract that one, the 1 is gone. When it's gone, you're left with I times this total. So on this side, if you subtract, this subtract that, cancel out, this subtract that, and everything in the middle is subtracted. So this has the n term, this also has n term. This second term subtract the first term, so the first term is actually left over. And the last term is subtract the, the last term is subtract the one before this term. So that one was left over. So you have this one and this one together with all the middle terms, which are involved Q. So then we have this formula for it after subtraction. What's nice about this is that in all the middle term has Q as a common factor, it has 1 plus I as a common ratio. So we're able to come up with a formula for this calculation. That's the geometric theory partial sum formula. The formula will have a name for it. It's the S sub n. Right? I would say that's actually 1 plus I to the power n minus 1 over I. That one. So since we got a formula for it, then the formula itself turns a little bit slightly easier, manageable. Even though you might think we lost that part, it's actually still it's in here. But at least the formulation, the equation itself looks shorter and more concise. Any questions? All right, so now the total future value having P dollar payment every single time plus Q dollar added in each subsequent payment. Now we have a formula for this, and that's going to be our formula. So that's our future value formula. Future value formula discounted for one, like this divide this by 1 plus I to the power n, and have this. Divide this by 1 plus I to the power n, and you have the present value. Divide that one by 1 plus I to the power n, you have this. Now that divided by 1 plus I, you have to keep it. That one is a single number, so that's why we have the Vn. V is actually 1 over 1 plus I. So that kind of shows the connection between the two formulas. I also kind of explained that if you have one formula, you automatically can have the other one. But this can't be done properly. So that's our formula. Now, a special case is what if we are being paid $1, $2, $3, $4, $5, and $10. So that's the increase in payment. Have we talked about this before? All right. So that would be a special case. Going back to this, what if this is 1? That's also 1 and 1. That's 1, 1 plus 1, 1 plus 2. Yeah, so it's 1, 2, 3, 4, 5 until n. And obviously they will follow the same pattern, therefore they will follow the same formula. In that case, this is also 1 who's strong. So you have S of n, 1 over S of n. So obviously we might have a shorter formula for this, not this formula. We use a shorter notation for it, which is called increasing sequence payment future value. We kind of combine some of the formula in the question to create a shorter formula if it's an increasing sequence of payment. Any question? So future value for increasing payment, present value formula for increasing payment. Then also for decreasing payment, we also have the same idea. If p equal to n, q equal to -1, and we have n and -1 to 1, so we have a decreasing payment. Then the present value for the decreasing payment is here. What's the present value? That was the future value for the decreasing payment. All right. Any question? That's I didn't see us using that formula as often, but having a short formula would help. Let's see how much time we have left. But you're right, we're using a lot of formulas. Sometimes I think we really need that many formulas for like whatever the calculation it is. But try to think of the connection of the formula. Try to remember 1 or 2 formulas. Try not to get overwhelmed by the sheer amount of formulas. Eventually, end up being not as useful if there's too many formulas. All right, so let's look at this one. Susan received annuity for her 18th birthday. The annuity pays $2,000 on her 19th birthday and then has an annual payment on each of her birthdays through her 35th birthday. I never received that kind of birthday gift. All right, so each year the payment increased by $500. So she's being paid at $2,000, $2,500, $3,000, and so on. So you can imagine the money grow, and then by the time it's 35,
How much that would cost?
that's right. We are finding it out. We want to find the value of the annuity on her 18th birthday. So we'll know how much they worth after we calculate it. So according to this calculation, P equal to 2,000. The increase is 5,000 each time. So P equal to 2,000, Q equal to 500. And 18 to 35, there's no payment, that's 18. 35 minus 18, there's 17 payments. So total number of payments is 17. Are we okay? N equal to 17, P equal to 2,000, Q equal to 500. So if we grab those key components, we can then apply the formula for the future value, for the present value calculation. So I copy over the present value calculation for IPQA. I means increasing in my mind. That's increasing the book. You can read the book about the naming of it. Q is 2,000, that's 500. That's the present value calculation. So we're going to type that. This is a 2,000, and this is 17. The interest rate is 4.2%, and you put in all these calculations there. That's the formula. Remember the A formula was 1 minus 1.042 to the power of -7 over 0.042. Remember the formula there? This A formula, you can't get around it. You have to somehow remember the formula. The total calculation gave us 66,843 cents. Any questions? So that's the total present value. It is a lot of money. Any questions? That's the formula, using that formula. Let's see, question and answer with that formula, increasing frequency of payment. Anything else? I think they are quite similar. Let's try one more example. So this is you may have to look at the wording of the question and think about does the quantity increase or not. If you're trying to find present value or purchase price, we do have to consider the interest rate. But if there are also situations we let money sit there and there's no interest. All right, let's look at this question. At the end of each year, Mr. Down deposits 6,000 into an investment fund. The fund pays out interest each year at an annual effective interest rate of 6%. Mr. Dunn is only able to reinvest this interest rate at an annual effective interest rate of 4%. So We don't exactly have 6% interest rate, but we're being paid that much, and we can reinvest it, so the money is not sitting there, not growing. So we try to make the money grow. Assuming Mr. Down contributed to make his 6,000 deposit for 20 years, that he always immediately deposit all the interest paid out into the 4% account, and that he makes no withdrawal what accumulated value of Mr. Down's investment at the time of the last deposit. So you might have to rethink of what we're talking about, like how many accounts are we talking about? Here we have two accounts. One is the account, the investment fund, which pays interest every year. So the money did grow in the investment fund, but he did not let the money sit there to grow interest. You can say to actually get money out of the 6% account. Are we okay there? So he has two accounts. One is the 6% account, one is the 4% account. He takes the interest amount out of the investment fund and invests it into a different account, that's the 4% account. And then that one is growing as time goes on. So this is what happens. In the investment fund, he deposits 6,000 every year for 20 years. In the saving account, which is a 4% interest, 6% is the 4% interest. He takes all the money from here and then saving it in here. So at first it was 6,000 times the interest rate 0.6 interest rate. So 360 is what he gets out of the investment fund every year. Are we okay there? So he decided, I'm going to put those 360 in here. So 2 years later, he deposited another 6,000. So if he actually have how much interest? 12,000 in this account. So 12,000 times 6% on here is 720. That is deposit in this new account. Now this account, the money it keeps growing at that rate. The balance sheet keeps. Are we okay? All right. So what happened there is that the interest did not stay in this account. So his final quantity is 6,000, 6,000, 6,000 times 20. There's no interest in here because he withdraw the interest and deposit into a different account. Are we okay there? So we want to find the total accumulated value. One is a 20 times 6,000. In the blue one, there is no interest accumulated because interest is not in here. Now the second account, we're saving $360, 360, 720. So 360 is increasing at a ratio, right? So 360 times 1, 360 times 2, 360 times 3, and then 360 times 20. That's what happened there. So this is an increasing sequence, which is in the sequence of 1, 2, 3, 4, 5. That's what we're using. So we're using the IX formula for this case. Any questions? The IX formula is the future value of 19 payment there. The interest rate is 0.04, which is the saving account interest 0.04 minus 19 over 0.04. And that's how we can calculate if you invest it 1, 2, 3, 4 until 20. But then of course we got 360 as the actual fraction ratio. That total, and then we add these two together. Any questions? All right, as you can see, this is the interest. Actually, it's not small. It's very big value. It's 120,000. This is 88,000. Even if you only save your interest every single time you're saving, you're still making a lot of money. Second question. So we do have to watch out how the saving is moved in between the accounts, and which one have interest, which one does not have interest. All right. So far we were using annuity immediate formula, but sometimes we do have a arithmetic progression payment with annuity deal. So what if we are paying not from, so the payment's not starting from 1, but starting at 0. Then we have to do what we call annuity deal formula. Those are the two formula we derive it. I think it's similar to the annuity immediate formula. That one was over here. It's one period earlier. I guess you can just use annuity immediate formula, discount it for one time period, and that should be the annuity due. That's what I think is how it is. Okay. That's this is how it is being calculated is equal to the annuity immediate formula times 1 plus I. So what it is. So we can simplify. It looks very similar to the formula in the annuity immediately, except the annuity notation now. Any question? Let's see how they're being applied in the actual question. Please work out those assignments. I mean, when you actually work out a question, it's different when you only talk about formula and then the examples. You can also work out these examples without looking at a solution, then you get some idea about how different our understanding is from what was supposed to be the understanding according to the book, so that we might be able to find some reasoning in the whole logic. The last part of the textbook. I want to try to finish chapter 3. The last section of chapter 3 is yield rates example involving annuity. So kind of like calculation of the interest rates for a problem that has annuity. It's most of these questions in this section are pretty hard to solve analytically by hand. You have to learn how to use your calculator to solve interest rates. Many times it's the internal rate of return, internal IRR. That was the one single method that allowed us to solve. You have a question?
No, we were just talking about IRR a lot in finance.
Right.
We calculated in our class today.
Right. So I see a lot of questions. The equation itself is not a single lower degree polynomial, like higher degree polynomial, or degree that's negative, which means you have division as fractional function, rational function. They're really hard to solve by hand. Most of the you can use Excel. Yeah, but the VA2 calculator really solves many of those scenarios. Okay. Let's at least look at one example. So here is Malini pays 24,000 and receive a 15 years annuity with end of year payment of 2,100. What is the annual yield on this investment? So assuming that we don't know the interest rate, and we're like, what was the interest rate that produced this kind of outcome? So here we are. So the 24,000 is the price of the annuity. So that's supposed to be the present value, right? All the 15 payments that you are to be paid, 15 payment of 2,100, their total present value should equal to the 24,000. That allows you to set up the equation, right? That's their equation. So visually, it's going to look like this. That's how it is. 24,000 equal to 2,100 times A15I. So there's a slight problem. We don't know the I, so our process is trying to find a way to solve the I, and that is something that is better solved with our calculator. So how do we solve this? You realize that A15 is 1 plus 1 plus I, so the negative 15 over I. So if you multiply both sides by I, you end up having this equation. So essentially, the solution for this equation is the root of a function. So you set up this as your function. You can divide them all by 100 just to make the equation, make the function a little bit less complicated. So we end up having this. Solving this is not easy. In the book, there are two methods. One is trial and guess and try. You figure out some reasonable x value, reasonable interest rate I, and try to enter it to see if it's positive or negative, right? The closer it is to 0, we're supposed to make this equal to 0. The closer it is to your final solution. It was supposed to be interest rate. You can try a couple combinations like 0.5, 0.6, 0.7 to see which one's closer to 0. And then you can zoom into that solution, right? If your calculator accept function, that makes it easier. Otherwise, you have to enter a lot of calculation. The second method is the Newton's method. Remember, we find the derivative, and then we identify the tangent line, that the tangent line x value, the tangent line y value equals 0 to find the root of the tangent line. And then we start from there to see how close it is. And then we find another tangent line and so forth. So repeated calculation of tangent line. That was Newton's method. All right, now down here is our solution using the calculator. And you can do the time value, use the time value calculation. You use the end mode, make sure you use the BTN, make sure it's end mode, and then you have the number payment set up to be 1, and here's what we're going to enter. We're going to have a present value, which is the price that we pay. Since you're paying money, we're consider the value to us is negative. So we have negative 24,000 is our present value, and 15 is our end value, and then 2,100 is going to be our payment value, and your future value is 0. Let's assume after all the payments, you're paid off the 24,000 value, and then you let the computer calculate interest rate, and that you're going to get interest rate calculator from it. Have you done? So I feel like this is the kind of question that will be not very complicated if you are using a calculator and follow the cash flow. But with a regular algebraic method, it's really hard. So the BA2 calculator does a lot of questions for us. Any questions? Yes.
Why do you have to change the 24,000 to negative?
That?
Yeah.
Because you're gonna have balance. I mean, on your entire timeline, some of them are positive, some of them are negative, so the full balance will be 0. So if all your payment of 21,000 are positive, then the initial present value has to be negative. Or you can look at this equation. You see, if you move this one over, it will be 21,000 a this 15 of 21,000 payments, and it's minus 24,000, right? If you move this to 24,000 will be negative, and this will be positive. If you move this one over, the 24,000 will be positive, and the payment of 2100 will be negative. But as far as the calculator, I don't think it allows you to make the payment negative, and I don't know, are we allowed to make the payment? If we are allowed to make the payment negative, then this can be positive, this can be negative, make negative 2,100, and you make the number payment 15, it'll be the same solution.
Yes, I just tried it, it's the same.
Right, so they cannot be all positive, because it won't balance out. Theoretically, you're paying 24,000. If the money is out of your hand, to you, it's negative, right? Right? And then the immunity is what you are paying, and so the 21,000 is people giving you money, so to you, it's positive value to you. So in that sense, you can, as long as you stay with one single person, the in and out will be balanced. If you go, sometimes on your standpoint, sometimes it's from the bank statement. If you go back and forth, then there will be confliction. But the whole idea is that since the future value is 0, the money has to come out somewhere. So some of them are positive, some of them are negative. They cannot be both negative and positive. One way or the other, the money has to come out somewhere and go away somewhere. Right, that's it today. Hopefully we'll look at all the other assignment. I'm hoping to end the chapter 3 because I feel like if we're finishing 10 chapters, we probably have to squeeze our time somewhere. I want to look at the academic exam just to have a clear idea what we're supposed to learn. And obviously our time does not allow us to study every single detail from the book, so we try to utilize what's really necessary. And I'm probably going to skip some part that's not very useful. Okay, so the first 3 chapters is very important, so I think we're going to have to go through the whole chapter. Any questions?
Did we go to the testing center or did we take
Yes. Are you ready? Yeah, whenever you're ready, schedule the time, let me know the time. I have to guarantee that I submit exam before your exam time, so they'll have it printed. Yeah.
Okay.
Yeah, as long as you let me know the time, I'll make sure it's made. I'll make the exam on my computer and submit it to their computer.
Okay. Super.
Can we accept the